planar robot example. In this case, we want to do part C, which says provide equations for L and theta in terms of x and y. Are these equations valid in any quadrant? So again, just keep refreshing you. One-link planar robot starts at the origin, ends at points x and y. We already determined that we can get x in terms of L and theta by using that L times cosine theta equals x and L times sine theta equals y. But now we want to go the other way. If we knew what x and y were, could we figure out what L and theta was? So let's do L first, because that seems really easy to think about. So if I have this and I want to find L, what property links these things? Well, this is a right triangle with sides x and y and hypotenuse L, so I know the Pythagorean theorem must work, that L squared must equal x squared plus y squared. And then I can just take the square root, and get L. And since L is a magnitude, it's always positive, I don't have to worry about taking the negative root. It's always going to be a positive number. Alright, so that one was pretty simple. We figured out our equation to get L. Now theta. To find theta is going to be a little bit more difficult, because not a simple relationship there, but we have to think about what trigonometric functions would relate x and y together that involve theta. We've used cosine, which involved x and L. We've used sine, which involved y and L. So if we start listing out our functions, we knew that cosine theta is adjacent over hypotenuse, so that got x and L. We did sine theta, which got y over L. Wow, I really just wrote those backwards on here, so that could be confusing later. This is, of course, x, and this is y. Y is in the vertical direction, x in the horizontal. We're not doing anything crazy here. These still match up. So the other function we use a lot in trig is tangent theta. And so what is tangent? Tangent is opposite, which is y, over adjacent, which is x. So that's a good way to we can use that in trying to find theta. That tangent of theta is equal to y over x. Well, then how do we get tangent by itself? Well, to do that, we would need to do the inverse of tangent. So we would say theta is tan inverse of y over x. This is also called the arctangent. And it means basically, given the opposite and the adjacent ratio, whatever that is, what angle does that mean? Which is exactly what we're trying to find. What it is not is 1 over tangent of yx, or, so we don't want to get it confused with that. That's the inverse. That would be inverse. That is cotangent. It's also not tangent Actually, that's not true. That's not cotangent. This is cotangent. Tangent of x over y. That's what cotangent is. This would just be the reciprocal, a different function. Actually, both those are true. Okay, so we want to not, so it's not those things. We don't want to deal with it. This is arctan. And so that would get us theta. Now the question is, do these work in both quadrants? Do these, I say both, do these work in all quadrants? So for the L equals the square root of x squared plus y squared, yes. No matter where we are, it's going to get us a positive number, which L, our magnitude of L is a positive number, so that works out. Theta equals tan inverse of y over x. Well, let's just do some examples and see. We assume it's going to work in the first quadrant, so if we gave it something like, let's just make this simple and say that x and y absolute value of 1. So quadrant 1 tan inverse of 1 over 1. So if we just do tangent of 1, whoops, tan inverse. So to find the inverse function, and since I'm going to get these out in radians, maybe it will make more sense. I'm going to actually convert to degrees because maybe we work better with those. And we can remember those later. So I'm going to change the mode to degrees. Because that keeps me from having to remember how big is pi over 2, how big is pi, that sort of thing. So we're in degrees. If we do tan inverse of 1 divided by 1, then I get that it's 45 degrees. And that's in quadrant 1. So that's good. If I want to do quadrant 2, what happens in quadrant 2? In quadrant 2, x is negative, so I have negative 1 down here. Y is positive, so I keep positive 1 there. And if I put tan inverse of 1 divided by negative 1, I get negative 45 degrees. Negative 45 degrees would be down here. So that's actually in quad 4. So that's bad. Well, how could I get it to be the correct angle? Well, I know what I need is something that's measured 45 degrees from the axis here. I need to flip the sign. So what I need to do is add 180 degrees. So negative 45 plus 180 would get me 135 degrees. And this is an instance where choosing the 1-to-1 ratio may not have been my best choice because you can't tell whether that's the 45 or this is the 45. But what we're really talking about is this 45 degree angle here. Is what's added on. So in other words, whatever this is what this one's going to be the similar angle. And I got that up off the page, sorry. Yeah, whatever this angle here is going to be the similar angle. So if this were 30 degrees, this part would be 30 degrees. So our total should have ended up, we would have gotten a negative 30 degrees and ended up with 150 degrees. Now that gets us something that's in the right quadrant. Similarly, quadrant 3, let's try one there. If we do a tan inverse, so in quadrant 3, x is going to equal -1, y is going to equal -1. So -1 over -1, it's not going to be surprising that when I put that in my calculator, if I have -1 over -1, it's going to see that the same way as 1 over 1, and it tells me that it's 45 degrees. So again, add 180 degrees, $225 should be what I'm trying to, would give me the correct angle over here. Quadrant 4, x is going to be +1, y is going to be -1. So we have tangent of -1 over +1. You already know what kind of happens with that. Negative on top, positive on bottom. We get -45 degrees, which is in the quadrant 4. So that's good. If we don't like negative angles, we can add 360. To get a positive number. And so if we added 360, then we should get 315 degrees. And so I've used one particular example where my base angle was 45, but that will work for any of our angles on here. Again, if you want to think back to our unit circle, if I got one where tangent of this is going to be -√3, but so is tangent of this one over here. And so knowing which quadrant I'm in tells me whether I'm at 330 degrees or 150 degrees. Or as my calculator would give me as -30 degrees. And similarly, it works for radians. So for theta, this is almost true, but must add 180 degrees if we're in quadrant 2 or quadrant 3. So that's our two base equations there, though. We've got this one works all the time. This one we may have to do adjustment depending on where we're at.